Taylor series. If a function f has a power series representation of this form, this is in closed form and this is in expanded form. Suppose f has a power series representation where the constants, the c0, c1, c2, c3, etc. are given by the formula Cn equals fn, nth derivative of function f evaluated a over n factorial. If that's true, then this power series is called the Taylor series for the function f centered at a. And if you look at these constants, c0 is then f zeroth derivative, means the function itself evaluated at a over 0 factorial, which is 1. That's c0. This c0 is fa, by the way. c1 is f1 derivative, that means f prime at a divided by 1 factorial, just that. So c0 is fa, c1 is f prime a, and if you look at c2 will be f prime double prime at a over 2 factorial, etc. So a power series represents a function f where the constants are found by this formula. If this happens, then this power series is called the Taylor series of the function f centered at a. Special case, if this center happens to be 0, everything same, the center is 0, then we get this power series representation for f where constants cn's are given by this formula, just the center is 0. That is called now Maclaurin series. Okay, different name, Maclaurin series. Okay, here's an example. Find the Maclaurin series, that means center is 0, of the function ex and its radius of convergence. And we learned in previous section how to find radius of convergence. Let's do it. So Maclaurin series, if you look at here, c0, c1x, c2x squared, c3x cubed, and as soon as we see a pattern, we may be able to write this closed form. So we need to start finding this constant. So I would start writing here f x, the function is e raised to x. So c0 will be then f0. So evaluate the function at 0, that means e raised to 0, which is 1. So c0 is f0, just using this formula, or I found here c0 is f at a. For Maclaurin series, a is 0, so c0 is just fa. I mean, you can use this formula over and over to find the constants. So c0, now f prime, c1 means f1, 1 derivative means f prime, so we need to find derivative here. So derivative of this function is itself, that means we can find c1. c1 is using this formula, by the way, that's just f prime 0 over 1 factorial, which is 1. So let's evaluate derivative at 0. So derivative is e raised to 0, e raised to x, so x is 0, just 1. Now let's find second derivative, from which we can find c2. So c2 is just using this formula again, that's the f2 means second derivative, now 2 factorial. It was 1 factorial 1, we did not write that. 0 factorial, which is 1 as well, we didn't write that, but 2 factorial is 2, which has we need to write. F prime 0 means just evaluate this function f double prime at 0, so e raised to 0 is 1 over 2 factorial. Okay, to match we can write 1 over 0 factorial here. This is 1 over 1 factorial, 1 over 2 factorial. Now let's find c3. Triple derivative is itself. From this we can find c3 using the formula. This is f triple derivative at 0 divided by 3 factorial, evaluate at 0, which is 1 over 3 factorial. Looks like we saw a pattern here. C0 is 1 over 0 factorial, C1 is 1 over 1 factorial, C2 is 1 over 2 factorial, C3 is 1 over 3 factorial. So this 0, we got 0 factorial on the bottom. 1, 1 factorial. 2, 2 factorial. 3, 3 factorial. And the top is always 1. That means if we find Cn, if we keep going and find Cn in this way, Cn will be what then? 1 over n factorial. Okay, thus we can write the Maclaurin series for Ex. So Ex is, in fact, if we write down the expanded, that's C0 plus C1x minus A is center, plus C2x is squared, plus C3x cube, and forever. Maybe here is the nth term and infinitely many. So this is Maclaurin series that we learned here. For function, C0, C1x, C2x squared, C3x cube forever. That's Maclaurin series. And which is, in our case, C0 is 1 over 0 factorial. So 1 over 0 factorial. In fact, since we know Cn here, we don't have to write those, because this Cn, that represents all the numbers n. I mean, this one is true for n equals 0, 1, 2, 3, all the way. So in this case, we can write the closed form. So I'm writing this closed form, n from 0 through all the way infinity, and that's this general term, which is Cn xn. In fact, this closed form represents every single term. If we take n equals 0, here we get C0, C0, x0. x0 is 1, C0, just first term. When we take n equals 1, we get C1, x1, the C1x, the second term, etc. And we know the value of Cn. Let's put that. So this is n from 0 through infinity of Cn is 1 over n factorial. So we can write xn over n factorial. So Ex, this exponential function, is given by this Taylor series expansion. And this Taylor series is about center, about 0. So Maclaurin series, by the way. Xn over n factorial. Now next, the question asks us to find the radius of convergence, and we know how to find that. If you recall correctly, this is, so we find what is that, by the way? The radius of convergence was limit n going to infinity of absolute value, but in our case everything is positive, so we don't need that. That was, if you recall correctly, Cn over Cn plus 1. Okay, and in this case Cn is 1 over n factorial, or here 1 over n factorial. So limit n going to infinity of Cn is 1 over n factorial divided by Cn plus 1. The next term, Cn plus 1, would be 1 over n plus 1 factorial. So 1 over n plus 1 factorial. And by the way, n plus 1 factorial is maybe written in this way. N plus 1 factorial is n plus 1, 1 less n, n minus 1, n minus 2, all the way to 3, 2, 1. To cancel n prime, we can just leave here n prime, factorial, not prime. So n plus 1 factorial is n plus 1 times n factorial. Okay, we can go all the way, but that way we can cancel n factorial. So n factorial, and here is n plus 1 times n factorial, that cancels. That leaves 1 over n plus 1. So just do it, okay? I don't have room here, but this is just 1 over n plus 1, and when n goes to infinity, okay, when n goes to infinity, so let me see, n going to infinity, this one goes on the top, so it comes out to be n plus 1, not 1 over n plus 1. I was wrong, because 1 over n factorial, so let me write over here, times, when we flip this bottom, 1 over n plus 1 factorial, so n plus 1 factorial goes on the top, that is n plus 1 times n factorial over 1, this one cancels, just n plus 1. That means when n goes to infinity, the whole thing goes to infinity. So the radius of convergence is infinity, means this power series is defined everywhere. Infinity means radius big, really big infinity. So this expression, the Maclaurin series for this Ex is defined everywhere. Okay, so we can find Maclaurin series in this way. Let's look at some important Maclaurin series and their radii of convergence. We just saw this. For Ex, in closed form we can write this, or in expanded form, this is the way, and we just found that radius is infinity. That means for any x, this series has a finite value. This series converges. This series makes sense for any x. For any value of x, we still get a finite sum. In the same way, here is another Maclaurin series for 1 over 1 minus x, we get this, but this is defined only inside -1 and 1. So the radius of convergence is 1. Okay, if we have a function 1 over 1 minus x, then we have a Maclaurin series in this way, and this is in expanded form. We've seen this before. It can be shown backward. So this is a geometric series, and as we saw in one of the previous sections, the sum of geometric series is just first term a over 1 minus r, because this is r, and first term is when n equals 0, x raised to 0, which is 1. So this makes sense when x is less than 1. When this common ratio is less than 1, then this sum makes sense. That means this has this power series expansion. So 1 over 1 minus x is same as this sum when radius of convergence is 1. So inside here, okay. In the same way, we can find for sin x. Sin x has this, and it also defined everywhere. So sin x has this Maclaurin series, cosine x has this, tangent inverse has this, and natural log of 1 plus x has this. We can find like what we, how we found here, it can be done. Okay, and these are, in a lot of cases, you might have to memorize or just get used to it. These are base functions. Based on these, you may be asked to find Maclaurin series for other functions. So why we care about this? Look at here, natural log of 1 plus x, this is not a nice function. If you integrate, it's really hard. And if you have to integrate twice, or if you have to differentiate several times, it's really hard to work with. But when we write a power series for this function, pretty much a power series, we got infinitely many terms, but with like 10 terms, we can pretty much get this approximation. But these are pretty much, this is a polynomial. We got infinitely many terms, but still a polynomial. And we can easily find the derivative, we can easily integrate, and we can easily do other things. That's why these Taylor series are important, or Maclaurin series are important, because we got just polynomials, and polynomials are the easiest functions to deal with. Watch more videos, examples on my website.